This is Jack Creel, and I'm just going to be running through the calculation answers of mine for the second homework assignment. So the first problem, 2-24, is just wants us to derive the differential heat flux equation for a cylinder. So we start with the overall energy balance here. We can break up big Q into little q times area. Same things with energy can become little e times volume, and it's steady state, so we know that this is equal to 0 on the right side. Then we're going to sub in this heat flux equation we know in for Q here and here, and keeping in mind that these are done at specific locations in space. Plug everything in, and then once it's all plugged in, we can divide by all this volume term, multiplying the energy term over here. And once we divide and cancel, we'll be left with this term multiplied by the K and the R as well, but this term, and we need to get this term from delta notation into our derivative notation. So I didn't write it out explicitly, but that would be done by doing the limit as delta R goes to 0, and you would get this from that. That's the final answer. That's all we needed, was just to derive that. For 2-66, it's talking about a flat plate solar harvester, and it wants us to do a few things here. First, we're going to get the temperature profile and then the heat flux. So we list out our assumptions here. Most of them are pretty basic, listed in the problem statement. And then we start with the basic steady state one-dimensional differential equation here. Integrate once and then twice. And then we use our boundary conditions to find the expressions for those two constants of integration. And so we knew the temperature, and we also knew the heat flux at the top of the plate harvester. And so once we do all that, we'll have our temperature profile here. And then we can find the heat flux by factoring in, we have to factor in the convection terms, the radiation terms, and the incident radiation terms here. And we'll find that the heat flux is 244 watts per meter squared. Then for the next one, 2-102, it has a few parts, and it's just asking us about wire and water. So the first part is going to want us to find the differential equation and boundary conditions. It's pretty straightforward. Once we know our assumptions, it doesn't take a lot to write out this differential equation here, and the boundary conditions are given pretty explicitly in the problem statement as well. So we know that at the interface between the wire and the water, that the heat flux due to conduction is going to have to be equal to the heat flux due to convection, and so that's written out here. And then the second boundary condition is going to be the symmetry, since it's uniform initial conditions, and then it's the same things happening at both sides of the wire. We're going to have a symmetric profile there. And then for part B, it wants us to actually find this temperature profile, actually write it out in terms of our variables. So we'll do that by integrating once and twice. And then we have to find the constants of integration again by applying our boundary conditions. And that's done here. Our boundary conditions were written above. We just need to apply them here. And we'll actually find that C1 is 0, so this term goes away, and C2 is worked out down here. Rearrange, and we'll find our expression for the temperature profile right here. And then in the last part, we just need to determine the temperature at the center of the wire. So the center will be where the radius is equal to 0. Plug in all the values from the problem statement, and we find that the temperature at the center is going to be about 125 degrees Celsius. The last calculation problem here, 14-40, was talking about a glass of water in a room, and it was just talking about some equilibrium things here. So the first part wanted us to know wanted to find the mole fraction of water vapor in the air. And I just know this equation. I believe this is from Raoult's law. If you say X, the water mole fraction is pretty much 1, then you would get this. The vapor pressure of water over the total pressure is going to give you that fraction there. And there it is. And then for part B, it wanted us to find the mole fraction of air in the water. And so for that, we're going to use Henry's law here. There's a table giving the Henry's Henry's coefficient values, and I used 290 because our actual value is 288 Kelvin, but the table did not go below 290, so I couldn't interpolate. And found a Henry's constant value of this, had to convert it into kilopascals to make our units match, and just worked out, plugged in, chugged the equation, and found this value for the mole fraction of air in the water.